question comes because of me. Because of me not really giving you the whole details. Somehow some important detail is missing in market switching. So now we discuss it. Let's see that she's not here. And well, and then we go on. Right? So we go on with the asset pricing. Well, I mean, when we did the market switching model, then I assumed two states. Right? And maybe this question was that let's say that, well, sometimes it may happen, let's say we have the asset return, I, and we have alpha st, plus say beta t market return, plus the residuals. I just run it very simple, right? So without the full factors, right? So just one factor one. Okay? So beta, let's say st. And then we basically assume that st has two states, 0 and 1. And then you have a high and low alpha, right? Sort of a high regime 0 and regime 1. Sometimes this happened, beta was high, sometimes it was low. Right? So that is what it basically saw. And then sort of here that you also have the variance, right? So the variance of I was also a function of st. So this was, when beta was high, then this was also high, when beta was low, then this was also low. Right? So remember. So her question was, so can it be that beta is high and variance is low? Yeah? So remember that when this beta was high, then sigma was, the variance was also high. Right? And then beta is low, then the variance is also low. You have just two regimes. Right? So our question was that can we have actually, say, beta high and sigma low? Alright? You clear? Or vice versa. So not two basically regimes, alright, but rather more than two. Alright, so four regimes. Right? So you see that this beta may be low and high, regardless of this being high and low. So there may be no limit. Right? But because here we have two regimes, then they are sort of forced to stay in these two regimes. But it happens so that one regime that you have high, beta high sigma, and in the other regime then you have low beta and low sigma. Okay? And thought, okay, so maybe let's actually generalize this and then have more than two regimes. So you simulated some data and I want to show you. So we write this, we don't take long. So we write some program so that you see what is happening with respect to the number of regimes. All right. And how to choose the number of regimes. So that's sort of what I'm heading for. Okay. So when I didn't tell you how to choose the number of regimes, that was the missing part. That's sort of part that I would like to look at now. All right. So, well, I mean, to generate some data to simulate, right? Then we do the following. So we do something very simple. Right? So we generate some random variable, let's say xt, and xt is sort of, well, let's say that this is time, right? Well, this is independent. Then independent. Across time. Alright, so that's sort of what we have. But then with different basically parameters. Let's say this is period 1, and let's say we go to period 10,000, many observations, and I break this sort of data into 1, 2, 3, and 4 periods. Right? So there are four different basically periods that I have here. So let's say here we have a mean, all right, and a variance. Let's say mean in period 1, so that's sort of what it is. So high, low, low, high, 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 low, high, low, low. These are the four regimes that we handle by. So we just simulate the data like so, right? And sort of apply Markov switching. Well, here we clearly know after observation 250, then we switch the regime. We know that, right? So that's known. And I want to know whether essentially this will be sort of the model that we have. The Markov switching is capable of recovering all of these switches. All right. So let's just start with this numpy numpy as np. Let's import matplotlib, pyplot as plt. All right. Import pandas as pd. Then we go to stats models. We go to the time series section. We go to the regime switching. And then here we have the Markov regressions. From that we import Markov regression. Okay. So that is, these are the packages now. So let's simulate the data. So that's sort of what we have. Let's set the seed so that we have the same data points. Right? We set it to say 42, right? So that we have the same stuff. The sample size is say 10,000, 10, 1, 2, 2,000. And now let's generate the data. So here the data will be we have a numpy, and then we concatenate, so we essentially attach a number of sort of quantities together. So we have to pass it as a list, all right? And now we start generating. So we say we have a random, and we go random. Let's say it is normal. Let's say normal. So tells us, okay, what is your location? The lock, basically grab it. And then we say that this is, first what did I say? 3. Right? Let's say we have 3. And then it needs a scale. And the scale, well, let's say this is SQRT of, that's a standard deviation. Let's say, what did I say? 0.5. Okay. Well, that's the first one. And now we need the others. Right, so let's take 4 copies. So from 3, then the mean goes to -3, and goes to 3, and then goes then to minus. Right. And then the standard deviation is 0.5, and then becomes square root of 2, and the square root of 2, and 0.5. Right. So these are all of the data. Let me make it bigger. Okay. Right, so 3 minus 3, 3 minus 3. So high, low, high, low. Low, high, high, low. Right? All of the 4 combinations that we have. Okay. Well, these are the data. Well, let's maybe plot them just to see how do they really look like. Well, I mean, so if let's run that. So, you have to also say the dimension, right? So you have to say the size, we want it to be 250. That is important. Right? So 250, 250, 250. So you have 4 data points that are together. So that's an array, right? What was that? So let's actually make it like series of data. We're using pandas series. So that would be easier at 3D work. Right? So these are the data, and we can now plot them. So plt dot plot series. That's better. happens that you have such a big shift. Alright? But here I make it like that so that it is really big, the change that you see. In the middle, the variance is bigger. You see there are more variations. Right? And in the beginning and the end, and the variance is smaller, that's 0.5, so you see a smaller variation. Right? Okay? So now let's say we want to estimate this, the model, which is simply normal, with Markov switching regressions. Okay. So because there is no exponential variable, so that was the point that it is actually simple, so that you see this is about the number of basically regimes. So here we have xt to be mu as a function of st, alright, plus some shock, alright, and let's go to t, where in t is assumed to be normal, and mu 0, and variance sigma squared this. Okay. That's what we so that's the model. That's a very simple mean. That's a mean regression. Just a constant. Okay. Now let's go on. And then estimate this using different Markov switching models. Different in the sense that we vary the number of regimes. Okay. And once we do that, then we also plot we can look at the series and sort of the estimates and so on and so forth. Right? So let's have the number of regimes, k of regimes. Alright, so then it will be a task to 2, and then we make a model. Right? So the model will be Markov regression. The endogenous variable is just 1. We don't have any exogenous variable, and the number of regimes is equal to k regimes. Okay? Well, that's sort of the two things that we have. Well, let's add a trend, and the trend is a constant. Well, we have just a new. Alright, that's what we have there. And then we also do the switching variance to be true. And that is by default false. For a trend, then the default is true. Right? So switching trend is true. Right? The exogenous variable is also true. The variance is false. So we just turn that on, not the others. Yeah, you understand. So let's do it carefully. So switching trend is also true. So that was my needed value. Let's get the results. Alright. And then the results are, well, we have a model, we just fit it. Alright. Well, look, maybe I just talk a little bit about the fit, now that they are given. So how you can do the fitting. So maybe at some point of time we will do a PhD and then sort of we're interested in some algorithms that we have. Right? Look, I mean, this guy is quite interesting. Alright. Specifically, what I'm interested in is the EM iter. You see this option, EM iteration. So this EM stands for expectation maximization. Right? Maybe you have heard it. So you know EM algorithm. That will actually take long, I tell you, but let me, expectation maximization indeed is an algorithm that came some years ago for optimizing a function which is essentially very dynamic or very complex. And it's actually very hard to do the optimization using the standard techniques. Well, this is not so complex, right? Because it's two regimes, so you have two means, mu1 and mu0, mu1, and two covariances, sigma1 and sigma0, so 2, so there are 4 so far. And then we have the transition probabilities, which you need the P00, right, so that's one parameter, and then you need the P10, so that you know how do you update, how do you go from one regime to the other, from 0 you go to 0 or to 1, or from 1 you go to 1 or you go to 0. Right? So there are just 6 parameters, right? So there are not too many. Right? What if the number of regimes increase? Right? So from 2 we make it 3, then the number of parameters that you have will also increase. It will be very big. Right? So little by little big. So if I have 3 regimes, then I will have 3 new, right? Plus 3 standard deviations. And then I need the transition probabilities. So that will be P00, right? And then how do you go from 0 to 1? Alright, so that's sort of if I have these twos, then I know how do I go from 0 to 2. So if I have 3 regimes. And so on and so forth. So you have to count and then see how many parameters in the transition probability you need to have, so there will be more. Alright, we can write them and see. And if you have 4, then these will become even more. Right? So the dimension of the problem simply grows very fast when you increase the number of regimes. And that makes the optimization hard. Alright? So if it makes it hard, then we need a very good starting point, because that's numerical. So here we have the starting parameters. If you have them by whatever way, if you can basically find the starting parameters, you feed them to the optimization problem, right? If you don't have them, all right, then you need some method. Find some starting values. These starting values are generally calculated using, well, here you can calculate them with, say, the expectation maximization, basically procedure. So here we can indeed choose this to 10. So that is basically calculates 10 different or 10 iterations it does for the expectation maximization. So because that's numerical, that's an interesting technique. Maybe you keep it in mind and read it for yourself. All right. When you're done with your courses, then read what is expectation maximization. That's an interesting algorithm. So it brings a lot of good knowledge to you. So that is what I want to focus on. So we basically say that the m iterations by default is 5. I will increase it to 10 because I expect that we need actually more regimes here. So that's number 1. And well, there is also another interesting option here, which is called, this is the search repetitions. All right. So what it does is that, so this is 0. All right. Well, so here, let's say you want to do a maximization problem, right? And that is sort of your after the global maximum of this point. That is basically function. It may well be that you start from here. So if you're starting point is here, then you go up here, and then you come there, and then the gradient or sort of the derivative is flat, and you're staying here. So that is the first starting value that we have. And then you get the local maximum. Maybe. So how to get around this problem? So maybe you need a different starting point. Right? So let's say we try another one. Let's say here. So that's number 0. Let's say you start from another starting point which is here. And you also end up there. Alright? So then if by chance, it's very important. Let's say I start somewhere here. Right? So that is what the third starting point. And then we'll be able to get the maximum, the global maximum. Right? So this search reps, alright, that we have here, indeed tries 0 number of different starting values for the optimization. Right? So they are chosen randomly. So randomly you pick something, and then you go up and down. So if I set it to 10, then it tries to start with 10 different starting points. And then from there, then it goes and then tries to do the maximization. So it increases the chance, well, it doesn't guarantee it for sure, all right? But it increases the chance that you get the optimum, right? The maximum. So that's the search rapid. So that's for the issue. And you have here. So I would say, so I do that in anticipation of the fact that I may actually do this regime switching with more parameters, right? I will tell you one of you. So you well, you can type it, but then let me just tell you. Right? So let's say we have some data which are independent across time, and they have, so they are normal distributed, all right, with mean mu and variance sigma. All right? And then here we basically have mu to be free in the first one. We have 10,000 observations, and I break it into 4 episodes. The first episode has a high mean, low variance, low mean, high variance, high mean, low variance, low mean, low variance. Right? But the data look like so we have generated the simulated. All right. So here and here the variance is small. Mean is low, mean is high, mean is low, variance high, mean is high, variance high. Right? And so sort of what I have here is I just want to sort of see, well, I mean, when we did our exercises with PACM, then we assumed 2 mistakes. And I never talked about how many mistakes you should use. So with the simulation, I want to basically tell you how could you approach finding all of those switches that we have here, right? So here we have different switches from one regime, then we go to another one, then we go to another one, and so on and so forth. I want to know, right? Well, here the data are generated in such a way that it's so clear that you have 4 regimes. But in practice, it may not be. Right? So I generated them like so, such that we sort of clearly see the different regimes shifts, right? Well, I mean, if you know that you have a regime shift here, then you just go and then take a shift, sort of a mean shift, right? So some indicator function, which is say 1 here and 0 otherwise, another one which is 1 here and 0 otherwise, and so on and so forth, right? So like a dummy variable approach, taking care of the dummy variable trap, of course, and then do the estimation together with the variance. All right? So that would be not a big deal. But because we don't know the number of regimes, then I just want to play around with the number of regimes and then see what happens. Right? So if you estimate it with 2, 3, 4, or 5 regimes, then this is going to be a little bit different. Sort of as time passes, sort of as we change essentially the number of regimes. Let's see. All right, so here we have res, and then I just look at the sum. All right, so they may take a bit of time. All right, so with 2 regimes, not much. All right, and then let's see. So it estimates 2 sigmas for us. All right. It captures the big mean and the small mean. So that is 3, which basically we have a high mean regime. So that is with 2 regimes, right? So when I have basically, I assume 2 regimes, which is wrong. That's a misspecification. If I do so, then I will get, here, well, let's look at that. We get a constant of almost 3 and minus 3, so 2 regimes. So it captures the one here and the one there, so these 2s. Then the means captures, but doesn't capture the variance, right? So the sigma squared, well, I mean, it gets something in between, so it doesn't know what to do. It gets us some number. It looks like to be in the middle. Right? So A is in the middle. Well, I mean, 2 plus 0.5, 2.5 divided by 2 is 1.25. Right? So roughly it gets 1.25 for both of them. So it gets the average. Sort of the average, well, it doesn't get all how does this model actually look like in terms of the transition probabilities? Okay? And if you don't mind, I will put this in a loop and for 2, 3, 4, and then estimate the probabilities, the transition probabilities, and plot them. Okay? So that we see them all. Alright. And let's do the following. So I would say 4K regimes in say 2, 3, and 4. Alright. Then do the following. So that is what we have. So the model is estimated, but the summary you can look at. Right, so that is what we have. And then well, let's specifically get the smooth probabilities. Well, I mean the probabilities that we have telling us that in which period you were in which regime. And then we raise, what was it? Smooth marginal probabilities. So that's sort of what we have. Alright. And let's just start plotting. So we're going to have a figure with some axes, which will be PLT dot sum plots. Well, let's say when we have two regimes, then so the plot we can have a 2 by 1. So that we see the two probabilities. So that will be well, if I have 3 regimes, then 3 by 1. So the K underline regimes. Alright, so and 1. Let's make this a little small. Okay. And let's set the fixed size to a total of say 12 and 6. Alright, that's good. That is somehow twice as the other. So that's the figure.
Like, if that's a plus.
So, yes, thank you very much. We always make this mistake. And there is another thing that doesn't like. K regime. Thank you very much. Good. I feel supported when you are here. Let's say for I in the range of K regimes. Okay. Then we go in axis I. Okay. And then plot the smooth props. Okay. Well, let's add a label. So let's go out of this, and then we add a label. The label we can have it like left string. Left string is well, that is regime of I. Good. So then what? The label will be shown, and then we see, oh, so this is regime 2, this is regime 1, and so on and so forth. We set this so that the legend is shown. Alright, so you should do it one by one. I in range, in. And then, well, let's add grades. I like grades. Alright. And then we are good to go. Alright. Well, that is sort of what we have. And then when we are done with this loop of this, then we say PLT dot show. Alright. So this is running. Okay. Once you're ready, then you let me know. And this was a missing link. If I was explaining this when I did the Markov switching, then would have misled later. Just nice questions. 5 or rather the average. Right? Let's look at the transition probability. So these are the transition probabilities. Right? So when we have two regimes, and that is, so here we have regime 0. We have high. So, no, in regime 0, then we have low. So that is here and here. So, which is great. So it basically captures. So you see regime 0, we have low. Regime 0, we have low with the probability of 1. Alright? Well, because we have a clear shift. Alright? So we really get the means. Alright? But we don't get the shifts in the variance. Alright? Well, here because we forced it to be two regimes. Alright? When we estimate 2, and then the focus is more given, so the difference here is more pronounced. Alright? So that dominates. So from 3 to go to -3, that's a big difference. So that's something which is much more serious in terms of a shift. So the two regime actually keeps the shift there. Yes. This is also different, but not so much. Right? So that this is there, but doesn't dominate somehow in 3. Right?
So what is
Good.
the blue line there?
That's the probability of being in which regime.
Oh, okay, so it, okay,
Okay, so these are the smooth probabilities. Right, so that is what we call the smooth. The probabilities of being in which regime at one time, point in time. And that is sort of very nice because in regime 0, which is low mean, well, in this period and in this period, then the probability of being in low regime is 0. You see?
yeah, yeah.
And otherwise, then it is 1. And well, the lower one is regime 1, so that's 1 minus the other. Right, so far, so this is not a good model. Right, so because we have 4 regimes, and where it doesn't take care of the variance shift. Alright, so we don't see it. We don't estimate the variance correctly. So, but as I said, so in practice, we don't really know. Alright, let's try a different one. So we here go to 3 regimes. Alright. So when we go to 3 regimes, then we get, so in regime 0, 1, and 2. Alright. So in regime 1, the mean is the low, minus 2.9. 2.9 and 2.9 in the other 2 regimes. Alright. So then there is a regime here where the variance is gotten in the middle. There is one where the regime is actually picks this, variance being 2. Alright. And there is another regime which picks the 0.5. Right? But there is another regime somehow. Right? That we, well, again, the algorithm doesn't know what I'm like. Right? So again, gets an average. Okay? So that's also not a good one. That's a misspecified one. But let's look at the probabilities. Alright. Let's look at the probabilities when we have 3 regimes. And they are looking like so. Alright? So, well, in the beginning, then you are in regime 3, regime 3. Alright? Then you go to regime 0, then you go to 1, then you go to 0. Alright? So that's sort of the 3 regimes that we have. Alright? Well, that's also a misspecified one. It also doesn't get the true shifts. Okay? Right? So, but it sort of understands that there is a break. But let's look at the last one. And the last one is sort of, well, it seems to be better. Right? So first we are with regime 0. Probably it's a high-low. We can look at the values. Let's look at the values of the estimated quantities for regime 0. Let's see. So that is with 4. Right. So we have high-low. We have high mean, low variance, and that is the first regime. Right. Then regime 2 is high. Alright, so we are in high here. Right. So that's regime 2 probability, which is this. You see, so this is high. have regime 2. Then we have low high, and that is here, right? So we have low high. Well, that's this. Right? So low high. And then we have the last, right? So the other regime. And let's look at regime parameters 3. So then we have low low. Right? So low low is this. The last. Low mean and low vary. And that's the last one where we have the set function going on. Well, I mean, there is a very short time period where the process from regime 3, from this one, right, so parameters regime 3, goes to 2, alright? But that's very small, you see, it's 1 day. So one day goes there and he says, this is the wrong place, it goes back here. Alright, so that looks like to be a very short time period. And you go up and come down. Yeah. So that's sort of what you have. And then of course we get the transition probabilities, right? Let's look at the transition probabilities from a regime, from the last one over here. For example, let's say we have 0, 0. Alright, so then we have all of the others. So everything actually is here is estimated. Alright, so we can basically take a look at and see sort of what is it that we have. Well, I mean, if you see, so the standard errors are at times not estimated correctly. Alright, so they're not really there for all of the models. These are the standard errors. They're not for all of the parameters. And that's a usual problem. Right? When the number of regimes become more, then the estimation becomes very hard. Right? So, but in any case, it seems that we are getting the true parameters out of the regimes. Right? Well, I mean, we know that it's not true because we know the true data generating process. If you didn't, then how would you go? If you didn't know the true data generating process, and I give you these 3 estimations, right? So 2 regimes, 3 and 4. Which one would you choose? Which is better? Let's say you didn't know the data. You know the data. So you know the regime 4 is better than that. Right? Now let's say I like it. You don't know it. Then how would you choose them? Choose the one, I mean one of them. That's a model choice. How do you choose models? If you have 10, which one is better? Let's say you have an AR1 and AR2. Which do you choose?
Balance between model fit and parsimony.
That's true. And how do you combine this model fit and parsimony together? Numerically? Use? That's true. So we can use it here. Right? So information criteria is not only for AR models, it's a general approach for choosing a model. Alright. So what I can do is, so here when I do the estimation, alright. So these are the results, right? So then I can get the AIC, which is the res dot, well, the AIC, alright? So that's the AIC of the model. I can also get the BIC. into the first graph. So if I have two graphs, then the first one has a type. If I have two subplots. Okay, and then let's run. There's one, that's the second model, and now we try with the next one. So now let's see. So this is AIC with two regimes, 3087. And that's BIC, 2011. 160. Oh, that became smaller. Yeah, the three regimes became smaller. And became even smaller with four. We can try five, but takes longer. So you use AIC to choose the number of regimes. So that's the answer to the that she asked me yesterday. Remember, model selection as mean set is always we use information criteria, parsimony versus good fit, and then go with it. So with this actually we choose model 4, not model with 4 regimes, not 3, not. Alright, so let's call this model choice reminder market switch. So today's date is 8. And we post it. Okay? You have questions?
Like how can the impression, like this graph, choose which one to be which regime, because like normally we would say 1, 2, 3, 4.
Oh,
Either the
yes.
graph is shown differently. And also like the second question is that if we give like for example like the regime 3 to switch with 1, I think it would be like yes, I mean like
Yeah, you
some
understand.
under-specified models may misunderstand it a bit because like the meaning is the same, just different variants.
I have two questions. Let me answer the first.
Yeah.
So the regimes are not ordered based on the probabilities. Okay, let's say here regime 0 seems to be here the one that is in the very last. Yeah. So regime 0 is not the one that has probability of that regime. Regime 0 is not the one that is indeed the beginning. You have to just check by yourself. So the regimes are not ordered in terms of numbering 0, 1, and 3, in terms of which is first. So this is just the probability. For regime 0 actually is the last one, which is this. So there is no order. But in this case, it may have made sense to do the ordering because the shifts between regimes is so stark. And you go from one regime to the other, then you stay there forever till you switch. So when you come from here to here, then it may have made sense to call this regime 0, then this is regime 2, but that is not the case, right? So regime 1 is the first, regime 2 is the second, regime 3 is the third, and regime 0 is the last, right? And that's sort of not made for this order. But you should always by yourself check, right? That sort of which regime is which. And now the other question that you had was that, well, let's say this was, well, let's actually change this to some other numbers. Okay? Maybe I understand your question correctly, so let me know. So let's say we change this to 2.9, and then here 1.95. Right? That's a switch. Or maybe 0.95 also, so a small change. So this regime and that one are very similar. Right? When we estimate the probabilities, then they will be somehow, they will not be so smooth that you stay in this regime if it gets it. Right? Then it may even be that it doesn't know which is which. very large, it's infinity, then we will get it. Alright? But I don't know if 10,000 is enough for this small change. Let's check. Right? So, well, I mean, if the parameters are too close to each other, well, I mean, then you don't know. Right? Let's say 2.95, and then here we also have 1.95. And we just do with 4 regimes. Okay. So that is just right. So this is how the data looks like. So from the last to the next, somehow there is a small change, but not much. Right? And now look, I mean that's sort of well, I mean this is regime 0 and this is 1. Right? So well, it seems that it gets. So these two it gets. Right? So they're different. Right? Well, cleanly we know that here we have the step function. So that's the beginning. Right? Then we have another step function that is regime 0, which is this. Alright. Now when we go here, then it's not clear. We are there. Alright. So mostly, if you look at this, mostly being in regime 3, whatever it is 0. Sometimes it goes, someone tries to go to the other one, but mostly gets 1. Alright. So 1 regime there. So here, well, this model actually doesn't identify 4 regimes. So these two are sort of merged together. You see that?
Yeah.
Because the parameters are too close. But if I increase 10,000 sample to say 1 million, but then you have to sit down and then wait for the calculation to go sort of 10 million, some are very large. I don't think it will actually do the computation, because that will be very heavy. So that is where we need you as data scientists to see what to do with all of these large data, and then maybe we'll be able to get it proper. Alright. So this small change doesn't make for a strong new sort of episode. Right? So that's sort of not so different. It's more or less the same as the previous one. Alright. Well, I mean, there is some precision that the estimates have, right? So that is what we have. Let me have it as before. What a nice question, thank you very much. Alright, so that is what we had. What I left out, I didn't highlight that you have to take care of the model choice. I just took 2 inventor. Right? Sometimes you may actually want to have more regimes and then see whether you can get the optimization right. Right? So if it is good, then you can rely on the AIC and you choose. Good. So what I want to do now today is just to go to asset pricing and then sort of just look at CAPM once more. Right? That's an important model. That's simple. People like it in academics. Right? And I want to define it for you. Alright? And you know how CAPM is. Right? So it says if you have an asset return is equal to, well, a linear combination of something. Right? So you have on the right hand side. And then we did an estimation of how French factor models. So factor models, indeed, I told you already. You know why they're important, so we looked at them. But I think because that's an important model, it may make sense to see under what conditions this CAPM actually holds. From where does it come? So if it is actually, so if you see the derivation, then you may understand what are its caveats, what are the problems that it has, and then potentially find remedies for them. So that's sort of the goal. That is what I want to do now. Alright. So, and then you will see that it's actually very easy. Right? So, I mean, where CAPM comes from is not actually a big deal. With a bit of tweak. So, I will actually leave some of the math out. You can work them out by yourself, or indeed, think of them a little. So let me start with deriving the Kaplan equation. Are you happy with this? Maybe before I do that, have you done any sort of math to see where this Kaplan comes from? And so Kaplan is a pricing equation.
Yeah.
And then why do we have it? From where does it come? Who said that the asset return should be related to the market returns? Why? You have done any derivation of that?
The professor did that, but you can do it against them, you can review it.
Very, very good. But the question is then how did the professor, you, who
He looked
did it?
Yeah. It's not from like, just like what you did yesterday, like from to risky asset, and then we add more risk-free asset, and then, and risky with one risk-free, and then we have the efficient ones here, then with the CAL, with the shock ratio.
Okay, I see. So that's a different derivation. So that is the classic one. And you do it differently. So you shouldn't have a different group. And that will be, I think, so that's good that you remember. So you start with the efficient frontier, and then you say that, okay, markets are efficient. If they are, then sort of under those assumptions, then you find the expression. Very good. Let me do it differently. Right. And then what you need to understand is nothing but to understand what is variance. Okay, so then you run the variance expression. So let's say you have two random variables, variance of a linear combination. And remember, that is a squared, variance of x plus b squared, variance of y plus 2ab covariance, right? So that you remember, right? Covariance of x and y. That's all you need to understand Kaplan. Nothing more. Well, let's say you have a portfolio, right? So with some underlying assets, N assets, and the portfolio will essentially we have some rates, some rating schemes. Right? So, well, let's look at the variance of the portfolio. Right? So what will it be? That is, well, the first one to the power of 2 rate and the variance of the first return, and so on and so forth. So here, let's say if I have N assets, all right, then I need to look at all of the variances and all of the covariances, right? So, well, then what we can do, so with the stuff here, then we can say that this is the summation over y equals 1 to n. The summation over j equals 1 to n, right? And weights wi times wj. So here we have weight vector, which is w1 of w, right? Times the covariance of return I and return j. Right? Do you agree? So these are one of the covariances. Are you happy with that? But let me maybe write this in this form, okay? So here it will be, well, I mean, let's say we define a vector, let's call it x1 and x2. Alright, or maybe r1. Let's really do it like this. Like the r's and w's and the weights. Okay? So that you sort of see what is going on. Right, so that is, let's say we have w1 r1, w2 r2. And that will be, well, I mean w1 squared variance of r1 plus w2 squared variance of r2 plus w1 w2 covariance of r1 and r2 plus w2 w1 covariance of r2 So, this I can also write like, this is like W1 times W1 times the covariance of R1 and R1. So variance, I can write the covariance. Covariance of one variable in itself, it becomes the variance. Right? And that's W1 times W. And then plus W2 times W2, covariance of R2 and R2. Right? Plus the other two terms. Right? So here we have first and second, all of the covariances, which are 4. So R1 with R1, R1 with R2, R2 with R1, R2 with R2. So all of them. And then you've got a row for an assets. Right, so that's the same as before. I'll just rewrote it. Good. So now that we are here, look, I mean, this is summing over J, not I. So there are two sums. One is on I, the other is on J. Right? So first I sum on J, so I is fixed. Then I sum on I. Right? So I can basically write it like summation of I from 1 to n. So we take WI out of the first sum, the inner sum, because that's the constant of Wj, the variance of I and Rj. Right, so that is equal to the variance. Right? We just took the W out. I haven't done anything. It's just manipulating this very simple formula for the variance. So now what I want to do is I want to divide both sides with sigma p. So further manipulation. So if I do that, then I will get sigma p equals summation I from 1 to n wi. So now I will write a bit sort of carefully. So here J was from 1 Wj covariance of Ri and Rj divided by sigma p. Yes. Well, you see, so I just divide both sides with sigma p with this sort of little manipulation. Right? So that's sort of what we have here. So in the denominator, then we have the covariance, sort of the variance of the portfolio. Okay. Well, let me also do this. Maybe I put it here. W. Okay. So that's sort of right. So that's Wi times this one. Right. Now I will do something. Right. And I want that you tell me, am I right? Am I wrong? Or basically what is going on? So is it okay or not? Right? What else is that? Right? So what I want to do next, where's my pen? And I want you to think of. So this that I have here is the covariance of asset return I and the portfolio. Do you agree with this? Well, portfolio returns, let's write the most explicitly. Right, so RP is summation I runs from 1 to n, WI RI. Do you agree with that? Right, I mean, that's sort of very explicit. Right. And very nice that you see it, but I will write it sort of in scheme. So then you the covariance of, and maybe let's call it J, so you see the link easier. So it doesn't matter. Let's look at the covariance of RI and something which is somehow related to regressions and understanding of, well, your understanding of regressions, right? And, well, of course, this is becomes very clean and understandable if you always remember that regression is a variance of the decomposition. Right? So that's why you have the y, it varies, it decomposes into this and that. Right? So that they're orthogonal. Such that the variance of y is the variance of the linear combination, right, plus the variance of the residual. Right? So that's the variance decomposition. Right? So if you remember this, then things become a little bit easier. Right? So in terms of understanding what is beta or what is beta. So very good. So this is not a C beta, it needs a sigma squared. Right? Down there, and this portfolio should also be sort of some market index. All right, so there sort of should be some market index, such that I could associate this with so the portfolio that I put together. I didn't tell you what is it. It is some portfolio. All right, some portfolio. For whatever portfolio, then this regression actually seems to hold. This decomposition seems to hold. All right. And I didn't tell you what are the weights. We didn't talk about that. We didn't say how do you get the weights. We said you have some portfolio, right? With some weights, with some returns, right? So now let's actually go on and then start to make it a little bit better, all right? So let's say you want to indeed, the expected value of the returns of the portfolio is the summation over J. Right? WJ is expected return of the individual. Right? So that's sort of what we have. Let's say you want to maximize something, some profit that you have. Right? Well, I mean, the returns, you sort of have the distribution, or you have their means. So if you want to get more returns on average, then you choose the W such that this is as big as possible. So we would like to maximize the returns. So that becomes, so somehow this is somehow going in the direction of this mean variance efficient frontier, but that's a different look at the problem. An easier maybe one. Right? For me, somehow I like that. Right? So, well, now, well, if I want to maximize this, right, then I need some constraints. I mean, first of all, I need the weights, well, let's say the weights, I need them to sum up to 1. All right? Okay? And well, another constraint that actually takes us to the CAPM being the market-based pricing equation makes us actually to say, all right, so choose this portfolio, all right, such that, well, let's call it sigma p, all right, that the sigma p is equal to the standard deviation of some market index. Right? So there are two constraints. The first is that the summation of the weights is 1, and the second is that the portfolio returns are in such a way that they have a standard deviation or a risk as much as the market risk. So to speak, this market, this portfolio will somehow fall maybe. Well, at least up to the second one, it falls on the market. The portfolio in terms of variance is the same. You can choose other things. But let's basically stay with this basically trade. Now we have to go and optimize. Right? Well, this is an objective function. I want to maximize the summation such that this works. Right? Well, so far so good. Well, so to speak, the sigma m is some number, some value, right? 2%, 3%, something. All right. When it places restrictions on the base, it will be a standard deviation. All right. That is what it goes. So you have two constraints, an objective function, and you have to set up a Lagrange. Right. Take the first of the conditions, the usual way you have, or you know. And so if you do the optimization here, all right, So then the solution will be in such a way that the rates, this is the rates that we have actually should satisfy the following. Let's say I have the returns on asset I, and then I have the returns on the market. Right? So now that's an equation. After doing the Lagrangian is not hard. All right. Will be say some Sn multiplied by, let me tell you what Sn is. Summation of Wi, what is Wi? These covariances, let's call them sigma 1 or sigma I. Well, that equation actually shows up in our calculations. All right. Sigma I, what was it? So at P, well, P becomes essentially M because we are focusing on the M, divided by sigma M minus sigma M. Alright? Well, that is the market, and that's the constraint that we have. Alright, that we have. So that is the market risk. Alright? And these are the covariances that each asset has with respect to the market. Alright? With the market that we have here. So the weights you should find so that this equation is satisfied. And where is M? Alright? So that comes out of when you do the Lagrangian, so that's sort of the sensitivity. And the sensitivity is the derivative of the expected return of the portfolio with respect to expected return of the variable at sigma. Alright, but this equation shows up. Whereas M is how sensitive the returns are with respect to the risk of the portfolio. Alright, that's as I said, so when you solve the optimization, then this will show up. Alright. Out of the optimization. Alright. Alright. Well, out of this sort of playing around with this covariance, well, having the variance like so that when we plug in our Lagrangian, we use this equation. This equation shows up there, and then we play around with that, and then we get sort of this. So that's the first sort of condition. Alright. So now, well, let me tell you where this is coming from. I posted it online, so you can read it for yourself. Alright, that is called Fama Macbeth. That's a paper in 1973. Alright, so I just summarize what is here. And that's the equation which I just showed you. Alright, and now I don't need to type. Now you're in a. Now I don't need to type. I don't need to write in the typing here. Rather, I can continue with discussing what is on the paper. You read it when you're somehow when you're on time. Well, now let's see. Well, I mean, we can manipulate the first order condition, which gives us some optimality for risk, for return optimization, return maximization. Right? So that's the first order condition, and that looks like this. Right? So what we can do is we can simplify things, all right? In the sense that we set this beta I, so that's the cap and the usual cap and beta that you have. And that's the understanding that you have from the cap and beta. This is what you told me that this is what. And if I do a regression, then the covariance divided by the variance shows up. All right? That's what we know. And indeed, well, this covariance is this summation. Well, X's are W's in my notation, so these are the weights. divided by that, and you can basically play around with this, right? So that becomes the covariance, right? Right, so you can basically divide this by the covariance, by the standard deviation, which is this, right? And what is that one? So if this was sigma squared, then I would have been happy. So I can take this to the power of 2 and divide that by sigma. Right, so divide, multiply. Right, so that is what we can do. So multiply essentially both of them with this. So we can multiply the numerator and denominator with that, this one. Then I get this sigma squared, then I get this sigma, then I bring it back to beta. So simply add this sigma squared, bring it in my equations. Right? So if you do so, I mean, let's see. So here we have the expected returns. So then we need some term. So we added here, well, that's Sm times sigma m, right? That is missing, multiplied by Sm. So that's the derivative that we have there times the market standard deviation times beta I, and beta I is here. So if I multiply, then this will remove. Right? So one of them will be sort of cancelling with the sigma m. Alright? What is beta I? If I multiply it with sigma m, so this cancels, and this remains. That's the covariance divided by sigma, which is, well, essentially this. Alright? That is what we have. Things actually match up, and then we will be back to the, well, the simple sort of setup that you have, say, if you have an expected return of an asset I, then it is equal to the market excess return minus some quantity, alright, which is the risk-free rate, essentially. They convert the risk-free rate. Alright? That's how the risk-free rate should be, right, based on the cap and mean regression, plus the cap and beta times some quantity, which includes the sensitivity. Alright? Well, upon doing some more manipulations, which I leave it for you to do and read, alright, then you will get essentially the usual cap and regression. And you have, say, the expected returns of your asset has some intercept, which is the cap and alpha, alright? So that's the risk-free rate, expected value of the risk-free rate. Times beta I, that's the scale. And that is the risk-adjusted market, the returns of the market minus the risk-free rate. But cap and well, the important maybe part for you is that we have some expected return, which one can manipulate it or maximize it under this condition, together with this sort of restriction that the portfolio risk is the same as the market risk. Then you come up with some Lagrangian, or some equation which identifies essentially the base. And then upon some sort of multiplying division and so on and so forth, then you get the capital regression as we have had it before. Well, that's not actually a capital regression. Alright. Well, that's not a regression model. It simply tells us that the returns on average have this specification. Right. Now the rest actually comes with respect to, so what is this beta? Alright, so beta, if it is an expected value regression, that's like regression that we have, then beta actually tells me that if it changes infinitesimally, a little bit, if the market basically return change a little bit, then you expect the expected return of asset I to change by beta. If this changes by 1 unit, right, then beta actually tells me how much do I expect this to change. Right? So sort of the usual sort of explanation that you have with respect to basically this equation. Right? That was a very maybe brief tour, such that when you start, when you're still reading the paper, it becomes easier. Right? And in my notations, then I use W, so I mean not with all of the other different way of looking at where CAPM comes from. Indeed, so if this portfolio is the market portfolio, the rates will be indeed optimal. All right. And then one can show, all right, that, well, let's say we look at the S&P 500, the index. All right. Then the index are based on the value of the company. So that's a value weighted index. All right. One can show that S&P 500 indeed solved this maximization problem. Right? So the weights sort of indeed based on the value, indeed maximize the returns. Right? Very well, sort of in some sense that we have here. All right, so that was a small derivation. Okay. Now the question is sort of, well, if I have a certain basically return and I have some market index, then does this equation hold? Do we actually have this holding? Or does the CAPM derivation, the way we just did it, hold? Right? Because if it holds in a given market, then you can use it to price the series. Right? Which will be very fun to check, to test econometrically, to see whether, well, you react, that's the theory. It tells us, okay, CAPM regression looks like that. I want to go and then test in the next section, so we have now a small break. In the next section, we will go and then test, and then see whether this equation actually holds. We can check Vietnamese data, if we can download it, to test whether CAPM holds in here. Yeah. Well, it was a bit dry, I suppose, but then next session will be more data and program. Or if we can get the data for us, so let's. Okay. So enjoy your break. And then get the
Cái máy giờ